Hey everyone, I wanted to do a video where we go through some more examples of using the subspace test to see if a subset is a subspace. So in the previous video that I have, which is linked in the description, we went through some pretty concrete examples where the subspace, or the subset rather, was defined, and we had to figure out if it was a subspace kind of from the definition of what it was defined as. And I wanted to go through some examples that go through the intersection, the union, and the sum of subspaces, and whether those things are considered subspaces, because they're a lot trickier to apply the subspace test. So we are given that S1 and S2 are both subspaces in Rn. Immediately we know that those three things that the subspace must satisfy hold true for S1 and S2. So the zero vector is in S1, the S1 is closed under scalar multiplication and vector addition, and the same for S2. So we are given this intersection of S1 and S2, and we're asked if that's the subspace, and luckily it gives us a definition for the intersection. It's basically saying here the intersection is defined as, so any vector x is in Rn, since our subspace is in Rn, and x is in this intersection if x both belongs to S and S1 and x belongs to S2. So if this doesn't make a whole lot of sense right now, let's sketch it out. I'm just going to use like a Venn diagram in this case, right? So let's scroll down here. This circle on the left, this is like subspace 1, and this is subspace 2. So a vector that belongs to both S1 and S2 is very clearly the intersection in the middle. So it means our vector x, all of those vector x, all those possibilities, they must be in between those. So the question now is this a subspace? So it all boils down to the basics, right? So number one, does the zero vector exist in the intersection of S1 and S2? Well, let's consider this, okay? The zero vector does belong to S1, and the zero vector also belongs to S2. So it would be considered in the intersection, right? Because the zero vector is in both of them, okay? So let's write, yes, zero vector is an element of S1, and the zero vector is an element of S2. Now, that might have seemed obvious, but let's continue. Okay, number two. We know that it must be closed under scalar addition for it to be a subspace. So let's let C be a constant, okay? Any constant that we want, right? And, well, we know that C times our vector x, okay, this is what we're trying to see. If, like, a scalar times a vector x, which is in the intersection, okay, is this in the intersection? Well, we know C times x is going to be an element of S1. It's going to be in subspace 1 because S1 is defined as a subspace. We know that scalar multiple times x is going to be in S1 since x is in S1 by the definition of our subspace. Right up here it says x is going to be in S1. And since x is also in S2, right here, and S2 is a subspace, that means that C times x is also going to be in S2, since S2 is a subspace. So since Cx is in both S1 and in S2, that means that it will be in the intersection because it's in both S1 and S2. Yes, Cx is in the intersection of S1 and S2. Okay, and last one here, okay? Number 3, let's check. So we need to see if we take a vector that is two vectors that is in the intersection and we add them together, will that produce a vector that is also going to be in the intersection? Right now we've only got one vector defined right now in the intersection, and we called that x. So let's define another vector to add to x. So let's say that y is in the intersection between S1 and S2. Okay, great. So let's think here. All right, x plus y. Okay, well, we know x plus y will be in S1, right? Since we defined y to be in the intersection of S1 and S2, this is telling us that y is an element of S as well as an element of S2. Since S1 and S2 are both defined as subspaces of Rn, it satisfies those three things already, one of those being vector addition. Since x and y both belong to S1 and S1 is a subspace, we know that x plus y is going to be closed under scalar vector addition for S1. We can apply the same logic and say that since x and y both belong to S2, that means that S2 will be closed under vector addition for x plus y. And since x plus y is both in S1 and in S2, that means that x plus y is in the intersection. So x plus y is in the intersection of S1 and S2. So we have checked all three of those things, okay? Yes, we know the zero vector exists. It exists in S1, it exists in S2, right? It exists in both, it's in the intersection. We did the same thing. Scalar multiplication, we figured out that it's in both S1 and S2, and then same thing for vector addition. Since it belongs to both of the subspaces in all of these cases, then we know that those three things will be in the intersection as well. So it satisfies all three, meaning it is going to be a subspace. So we can conclude the intersection of S1 and S2 is a subspace of Rn. Okay? Let's move on to example number 2. Is the union of S1 and S2 a subspace? And let me just write down the definition for this. So I've just written the definition of the union. The union is similar to the Venn diagram. Rather than it being the intersection of S1 and S2, the union simply means that it can be anything in either of these, S1 or S2. So it would be this entire Venn diagram colored in, okay? Something in there would be in the union of S1 and S2. Doesn't necessarily have to be in that intersection. It can be in either S1 or S2. And I've written that here. So the vector x is in the union of S1 and S2 if x is in either S1 or S2. Okay, well, let's think here, okay? Very clearly, you can think, okay, S1 is a subspace. Does the zero vector exist in S1? Yes, since it's a subspace, the zero vector does exist in S1. That means that the zero, we only have to show that it's in one of them. Since zero vector is in S1, good. We know that the zero vector will also be in the union. Okay? Now, let's jump straight away to vector addition. So this is where things boil down to be a little bit funny, okay? So since the vector in the union can be in either S1 or S2, okay, then if you were to add those vectors, will the result also be in the union? Now you might think, okay, let's take a vector x, and let's say that x is in S1, so it's in the union. Let's take another vector in the union, for example, y. And let's say that y is also in S1, because it doesn't have to be in S1 or S2. As long as it's in one of them, it'll be in the union, okay? So if I take x plus y, then since S1 is a subspace, vector addition should say that x plus y is also in the union. And that might seem true, but let's say that one of your vectors is in subspace 1 and the other one is only in subspace 2. If you add those vectors, does that guarantee the result will also be in the union? And the answer is no. And let's try to prove that with a counter example. So, for example, okay, let's consider that n is equal to 2. So therefore, S1 and S2, they're subsets of R2. And let's say that S1 is the subspace for all of the vectors which lie on the x-axis, okay? So we can very clearly mentally think, okay, if the 0 vector, the origin does lie on the x-axis, so the 0 vector is in S1. If you scale a vector that lies on the x-axis, the result will also be on the x-axis. If you add 2 vectors on the x-axis, the result will also be something on the x-axis. So the subspace S1, we know, will be the x-axis. For example, we know it's a subspace. You can apply the same logic for the y-axis. Okay, so let's consider, and I guess you should probably write this down. Actually, you know what? Let me write it down. Okay. Okay, I've just written down a mathematical way of expressing what we just said. Okay, so let's take 2 vectors now. Okay. Let's say, okay, we know that 1, 0, this is in S1, which also means that 1, 0 is in the union of S1 and S2, since it's in S1. Okay. We also know that 0, 1 is in S2, right? And I'll say the same thing. These vectors both would satisfy the definition for the union. It's in either of the subspaces, right? So if the union is a subspace, I should be able to add these vectors together and also get something that is in either S1 or S2. So let's try that. Well, 1, 0 plus 0, 1 is equal to 1, 1. Now, 1, 1, let's refer back to our definitions for subspace 1 and subspace 2. Well, it doesn't meet any of these, right? This is very clearly not on the x-axis or the y-axis. 1, 1, this is like 45 degrees from both of them, right? So it's neither in S1 or S2, which means that this is not in the union of S1 and S2. So we've just shown with a counterexample that the union is not a subspace. Great. Let's move on to the last part, okay? We are asked to, let me zoom out a little bit. So we are asked to show whether the sum of 2 subspaces is defined as a subspace, okay? And this is defined for us right here. S1 plus S2. So we've got a vector x is in the sum of these subspaces if x is equal to the sum of a vector from S1 plus the sum of a vector from S2. Okay? A little bit weird. So you might be thinking, how is this different than the intersection? So basically the intersection is like it has to be in S1 and S2, while C, or the addition of subspaces, is basically you can have any vector in the sum as long as it is a sum of something from S1 and something from S2. So one of them is the addition, the other one is it needs to be in both of them. A little bit weird. So let's think about this, okay? Let's go through the exact same process that we would. does the 0 vector exist? Okay. Is the 0 vector in S1 plus S2? Okay. Well, the 0 vector is in S1 because S1 is a subspace. And the 0 vector is in S2 since S2 is a subspace. Right? We know that the 0 vector plus the 0 vector is just equal to the 0 vector, right? So this here is something from S1. We're adding something from S2, and we are getting the 0 vector. So we are showing that the 0 vector is in S1 plus S2. So yes, the 0 vector does exist. Therefore, yes, the 0 vector is in S1 plus S2. Right? It's just 0 vector plus 0 vector. Something from S1 plus something from S2. We get the 0 vector. The 0 vector, by definition, we're adding something from S1, we're adding something from S2, and the result is something in the sum of S1 and S2. And they get the 0 vector. So yes, the 0 vector is in the sum. Okay, let's check number 2. Number 2, okay, we are asked, let's define a scalar C, okay? So C times X, where X is in S1 and S2. Okay, well, we need to figure out, is this going to be in the sum? Now, we know that X, from the definition, since X is in the sum, can be written as X1 plus X2, right? So we can do this as C times X1 plus X2. Zoom in here. All right. Let's expand this out. We've got CX1 plus CX2. Now, you can see a little bit more clearly here. Well, S1 is closed under scalar multiplication, right? So this first term in this addition is something from S1, right? Our second term here, well, scalar multiplication is also closed under, or is also closed for subspace 2, right? So this is something in S2. So we've just shown that a scalar times a vector in the sum. Remember, X was a vector that is in the sum S1 plus S2, and it follows this definition. We sub that in, and we've broken it down, and we can see that CX1 is something from S1, and we're adding CX2, which is something from S2. So CX is going to be in the sum. So let's write, therefore, C times X is in the sum S1 plus S2. Okay, and finally, last check, okay? We need to see if the sum is closed under vector addition. So let's define a new variable, a new vector, okay? Let's let y be equal to y1 plus y2, where y1 is in S1 and y2 is in S2. So very clearly we've shown here this is just another vector that is in S1 plus S2. Right? Follows the exact same definition, right? And of course y is a vector of Rn. Okay. So we need to figure out, is X plus Y going to also be in the sum? X plus Y. Well, X is in the sum, which means that X can be expressed as X1 plus X2, where X1 is in the subspace 1 and X2 is in the subspace 2. And we are adding, let's sub in, well, we know that Y, we said as well, is also in the sum of S1 plus S2. So it's y1 plus y2. Okay. Great. Now let's just do a little bit of rearranging here. And we've got x1 plus y1 plus, well, this is just x2 plus y2. Just did a bit of rearranging. And you should see here that, well, this first term, we've got two vectors from S1. X1 and Y1 are both vectors that belong to subspace 1. Since S1 is defined as a subspace, we know it's closed under vector addition, which means that this term right here is something that also belongs to S1. And you can apply the exact same logic to the second term. Since they both belong to S2, then the addition of those vectors will also be something in S2. So we've now shown that taking a vector x that is in the sum plus y, which is also in the sum, it all boils down to a vector that belongs to subspace 1 plus a vector that belongs to subspace 2. And that is the definition, right, of the sum of S1 plus S2. So we have checked all of these things, okay? The zero vector exists, it is closed under scalar multiplication, and it is closed under vector addition. So finally, we can conclude that the sum of the subspaces S1 and S2 is also considered a subspace of Rn.